Okay, it's time. Let me start the screen here. All right. Oops, not this one yet. Okay, good morning. So to start off today, I'll go over this agenda for this week. Okay, hang on a second here. Okay. So for this week, we have our first midterm this coming Thursday, okay, 2 days from today, 9:40 to 11 a.m. online, open book. It's going to cover chapters 1 through 6. Could be calculation and conceptual types. And there will be 4 problems for the midterm, okay? So yeah, please practice end of chapter problems. I've already provided you, I posted the end of chapter solutions for even number problems. So please go over those, practice those. Those problems are from past midterms. I think I mentioned this first week of class, right? That for my classes, not just this class, students don't need to hunt for my past exams because they are given, they are provided in the book, right? So again, those are my past exam problems as well as quiz problems. Okay, so please go over those so you can see the kind of problems I've given in the past for midterms as well as quizzes. Okay. In terms of lecture for this week, it's just going to be today, because again, Thursday is going to be our first midterm. We're going to start chapter 7, a big chapter on DC to DC converter, right? I'm hoping that everybody can attend, or everybody could attend the lecture and does not miss the coverage on DC to DC converter. That's very important, this chapter 7. If you understand buck converter, for example, from chapter 7, then you'll have easier time to understand the rest of chapter 7 as well as chapter 8. Chapter 7 is going to be non-isolated converters. Chapter 8 is going to be isolated converters. Lab number 6 this week, and the reports due this Friday. No quiz, no homework due this week because we have our first midterm again this week. And what we are going to cover in the lab this week is that we're going to cover performance testing and inductor current of buck converter. Okay? So more on buck converter for the lab today. And we'll be using LT Spice instead of ORCAD for today's lab. So make sure you have LT Spice ready in your laptop or computer or PCs. All right. Any question on the agenda? All right.
Hi, sorry, I have a question.
Yeah, go ahead.
For the midterm, is it going to be like a print, do scan, submit, or is it going to be like a Canvas fill in a quiz type?
So as I explained last week, it's going to be a file. So I posted the file. You can download the file, and then you just fill out you just write your solution on papers, and then scan them, upload them. Okay. Does that answer your question?
Yes, thank you.
Okay. All right. So you need to scan and upload your solutions, your answers. Okay. Anybody else? Okay. All right. If not, let's get started with our chapter 7. I already started the discussion on the first function of DC to DC converter, okay, which is providing us with DC transformer. Very nice, right? Now we have a transformer for DC because of this technology, DC to DC converters. And then also with DC to DC converter, we have the convenience of converting energy from a single source to several different voltage levels rather than having many or several supplies, right? Yeah, imagine if the source is, there's only one source, right, such as a battery, and then you have many loads to supply energy to, then you don't need to have multiple DC to DC converter. You could or you may have only one DC to DC converter to provide those loads. Okay, and for that you have to use the topology that we're covering in the next chapter, chapter 8. Okay. Oops, no, not yet. And then increase efficiency in offline power supply by bypassing the use of bulky and lossy line transform. So we talked about this in chapter, I believe chapter 2 or chapter 1, I don't remember exactly. So I'm not going to go over this again, right? The difference between linear power supply and switching mode power supply. Linear power supply, you transform first from AC to DC, and then you do linear regulator, which is not very efficient. Whereas switching mode, you rectify the AC first, then you switch it to the required output voltage, right? And by doing that, you get rid of the 60 Hertz transformer right there. So you don't have this anymore, right? So there's nothing there, right? You don't see any transformer here. Although you may see a transformer here in the DC to DC converter, but that's going to be relatively small transformer because it's going to be high switching frequency transformer. Okay. Okay, so this next topic relates to our lab today. So you'll be doing let's see, four of these out of 6. So these are the ways for us to evaluate performance of DC to DC converters. The very first one is efficiency, and then line regulation, load regulation, cross regulation only needed for isolated topologies. That's next chapter. Peak-to-peak output voltage ripple and dynamic load testing. So these are standard performance evaluations for DC to DC converters. Okay, so if you are designing as well as you're purchasing some DC to DC converters, these are some things that you would like to check, would like to test, right, to see or to evaluate the performance of the DC to DC converter. So let's start with the first one, efficiency. Definition of efficiency, it is the ratio of average output power in watts to average input power in watts of a device. In this case, DC to DC converter. Notice the keyword average, okay? Average power, both at input and output, okay? So you need to measure or calculate average power at input and at output of the device, in this case, DC to DC converter. It is a measure of how much average power is being lost in the converter, right? Ideally, all the power that is delivered by the source should be absorbed by the load, should be used by the load, right? But we know that's not gonna happen because DC to DC converter has losses, right? And therefore there's some amount of power lost in the DC to DC converter, right? So the amount of power being lost in the DC to DC converter would determine the efficiency of that DC to DC converter. So therefore it is important for us to be able to know this value, right? Mathematically, right? It's given by this equation. Efficiency is equal to P out over P in. Now, since we have DC to DC, so calculation will be straightforward. You don't need to deal with RMS values. Everything here is average values. You can see the bar on top of each of these parameters, right? V out average, I out average over V in average times I in average, right? These are all average values. Right? And I forgot to mention that efficiency is typically measured from some low load, such as 10%, to a high load, such as 100%. Keep in mind, I've mentioned this in the lab last week, I believe, that load typically means in power electronics, output current or output power. Right? So when it's stated 10% load, like there, that means 10% of full load current. So if the DC to DC converter is rated at, for example, 100 amps, so 10% of that would be 10 amps. Okay, 100% will be 100%, 100 amps. Sorry. So typically that's how we measure efficiency throughout range of the load. In this case, output current. Efficiency is commonly provided in percentage. So you just multiply this by 100% to give us the percentage that we get from the efficiency. Note that efficiency listed on data sheet may be either the peak efficiency or the efficiency at maximum load. So be careful when you buy a DC to DC converter. Of course, they would advertise, the peak efficiency, right? So you got to be careful when reading the data sheet of these of any DC to DC converter that you purchase. Make sure you know at what condition this peak efficiency is measured at, right? So if the data sheet of this DC to DC converter states that the peak efficiency is 94%, for example, at what load, was this being measured, right? Because it might be different from what you're thinking. Okay, so be careful. Here's an example. So this is very typical of efficiency curve of a DC to DC converter, right? And you notice that it's not constant. Efficiency is not constant. It starts low and then it goes up high, and then it start to slope down. Okay. And here's the peak efficiency right here. This is what they typically advertise, right? So in this case, the peak efficiency occurs around, I don't know, 12 amps or so, right? So make sure that you look at the efficiency curve. Before you decided to purchase a DC to DC converter, make sure that you look at the efficiency and make sure that the efficiency fits to your need, right? In terms of the application that you're going to use this for. Okay. So again, be careful on the peak efficiency that's being advertised. They want to sell their DC to DC converters. That's why they're listing the peak efficiency, not the full load efficiency, definitely not the low load efficiency, right? Here's an example. A DC to DC converter is supplying a 5-volt load at 10 amps load current. If the applied input voltage is 10 volts and efficiency is measured at 80%, then calculate the average input current. So what do we have here? Efficiency 80%, input voltage 10 volts, output voltage is 5 volts, output current is 10 amps. So the one thing that's missing is input current, right? Because we have the efficiency, output voltage, output current, input voltage. So 0.8, 80%, excuse me, equals to V out average times I out average over V in average, I in average. So we got V out average, I out average, V in average. So the only thing that's missing is I in. So therefore you can get I in from this simple equation. Okay. Any questions so far about efficiency?
I have a question.
Yes.
What normally determines like the full load current? Is there like a particular component that you normally rate it for, or?
Yeah, so when you're designing, right, you're talking about when you're designing a converter.
Yeah.
So when you're designing a converter, first of all, you're designing based on design requirements, right? So it's not like you select MOSFETs first or select components first, then you determine output power or output current. It's the other way around. You need to know the design parameters first before you select components. Okay, so before you design a buck converter, for example, then you would have to know, okay, what kind of output power does this buck deliver max? So then you will find out, okay, it's going to be 100 watts. So based on that, and then at what output voltage, right? Besides output power max, also output voltage. If let's say, okay, the output voltage is 5 volts. So then from there, we know that since the output power maximum output power is 100 watts, output voltage is 5 volts. Therefore, output current, 100% load or full load is 100 divided by 5, 20 amps. Okay, so that's what determines the maximum or full load current. Based on that value, then you would design, then you would select components, right? Based on what we're going to cover in this chapter. Right? There are some equations for you to select the proper MOSFET, proper diode per given current. Does that answer your question?
Yeah, thank you.
All right. So keep in mind design requirements first before you start selecting components. Right? You have to know that. Okay. Next, line regulation. Refers to the ability of power converter to maintain the output voltage even when the input voltage fluctuates. So line typically means input, right? From the line, line means from the input. Right? So again, it refers to the ability of a converter to maintain the output voltage even when the input voltage fluctuates, right? So majority of DC to DC converter, they are designed to give out or to provide constant output voltage, right? So this output voltage needs to be maintained at a constant value regardless of the change in the input, right? That's the ideal case, right? Doesn't matter what the input voltage is, but we know in reality, there's going to be a limit to this change at the input, right? The input will fluctuate as much then, or so much, then only certain value of fluctuation the converter can handle to maintain the output voltage, the constant output voltage. So that ability is called line regulation, the ability to maintain the output voltage at a constant value while we are changing the input voltage. That's called line regulation. Usually is given or calculated in percent as well. So percent line regulation is mathematically defined to be V out average at high input minus V out average at low input divided by V out average at nominal input. So when you test the prototype that you design or DC to DC converter that you purchase, that's how you would measure. This is how you would calculate percent line regulation. You would go to the lab and you would get 3 different values. Okay, there are 3 different values. You measure the output voltage at 3 different input voltages: high input, low input, and nominal. Right, and these are all average values. Okay, output voltages that you see here, these are all average values. And line regulation is typically provided on the data sheet as well if you purchase a DC to DC converter. So here's the diagram to show you what you need to do for line regulation measurement. Okay, I forgot to mention that as you are changing the input voltage, you want to make sure that the load is always full load. That's a must right there. Always at the worst case scenario, which is full load. Full load means 100% output current, right? That's what it means, right? I mentioned earlier that load means current. So that means 100% of the output current. You have to maintain that, right? And in our lab or in generally in power electronics lab, we're gonna have what we call electronics load that you learn already in the lab portion of the class. So it's easy to set that electronic load to the full rated value, right? By just, pressing the button or just turning the knob. Let's say this is 20 amps, so you just keep the amperage at the load using electronic load at 20 amps, right? So make sure you maintain this, all right? And then first you would, let's say, measure the output voltage, right? This is the output voltage. You measure the output voltage. When input voltage is minimum, you measure the output voltage, and then you change the input voltage nominal value again at full load, then measure the output voltage again. And then lastly, at maximum input voltage, measure the output voltage again. Again, all of these are at full load, right? So again, you get 3 numbers, 1, 2, 3, okay? And based on the 3 numbers, you can then calculate percent line regulation, okay? Here's an example. A DC to DC converter is rated at 12 volts at 10 amps. That's full load right there, 10 amps. 20 volts to 28 volt input. So you can see that this DC to DC converter is designed to take in input voltage from 20 volts to 28 volts. Okay. Output voltage is 12 volts. Remember that output voltage 12 volts, output current 10 amps max, input voltage from 20 to 28 with a nominal value of 24 volts. Okay, so we have 3 numbers already, right? V in min, V in max, V in nominal. Find its line regulation if at V in 20 volts, that's V in min. Output voltage is 12.29. At V in max, 28 volt, V out is 12.35. And at nominal voltage input, 24, output voltage is 12. All were measured at full load. Remember this, okay? Always measured at full load, okay? When you get those numbers, we already got those numbers, right? Let's say these are the numbers you got from the lab after you measure the voltages, then just a matter of a plug-in check now, right? This is V in max, V in low, V in nominal. Then you can see that for this example, percent line regulation is 0.5%. Any question on this? Okay. Oh, go ahead.
So to figure out the nominal voltage, is that coming from where you said that the input is 24 volts and output is 12 volts, or is that from the voltage rating of the converter?
Well, in this problem, it's given, right? In this problem, it's given input with a nominal value. So that's given. What about if you're designing one? If you're designing a DC to DC converter, then again, that's something that you have to know before you design it. You have to know that. Just like the output power that I answered, the previous problem, previous question. Sorry, somebody asked previously. So things that you need to know before you design a converter, they're as follows: V out, right? Percent V out, peak to peak ripple. So you have to know these 2, okay? And then P out max, you have to know these as well, right? And you can see from P out max and V out max, you get I out, right? So I don't need to give you I out max. This is going to be coming from P out max and V out, okay? Keep that in mind. Another thing that you must know is V in min and V in max and V in nominal. You must know this, right? Sometimes the customer just give you V in nominal. But if that's the case, that's good. If that's the case, that's actually good, because then it's up to you whether or not how far down you would like to choose for V in min and how far up you want to choose for V in max. But typically that would also give you the range of the input voltage and V in nominal. So this has to be given, right?
Why was 24 not used for the nominal value in the denominator?
No, the equation is asking for V out
in the equation there.
What equation?
Well, I thought you would divide by 24 the nominal value of the input.
No, you divide it by V out at nominal value.
Okay.
So let's look at the equation again. It's not V in that you put in. You're not putting V in, you're putting V out. V out at high input, V out at low input, V out at nominal input, right? So be careful, these are all V out.
Okay.
So if you look at the problems, focus on V out, not, I mean, V in too, but you don't put V in the equation, right? So let me just erase this. So I'm gonna circle V out in red. Right, the equation is asking for V out at V in min. Where is that? There's V in min right there, 20 volt. What is the V out at 20 volt? 12.29. This is the one that we have to enter, that have to put into the equation, okay? And then what else? V out at V in max. V in max is 28, isn't it? So at V in 28 volts, V out is 12.35. This is the number you have to put in the equation. And lastly, V out at V in nominal. There is our V in nominal right there. But what is the V out at V in nominal? 12 volts right there. So therefore, the numbers that you have to put in the percent line regulation will be these three numbers. All V out, 12.35, 12.29, and 12 volt. Is that clear?
That clears it up. Yeah.
Okay, good. Yeah, be careful. It's not V in that you put in, it's the V out. Okay.
So, Professor, when it says that the DC to DC converter is rated at 12 volts, is that coincidence or is it supposed to match the nominal output voltage?
Yeah, this is just coincidence, just to
Okay.
just to make it easy. Yeah. In reality, of course, in real world, when you input 24, but that's nominal, isn't it? When you put in the nominal input voltage, the output is not going to be exactly 12 volts. It's going to be 12 point something or 11.9 something, and very close to 12 volts. But this is like think of this one as the spec, right? So that's the data sheet value that you will be providing.
Does that mean the rated value is not always the nominal value, or not always the output when you input the nominal value, or do they match up?
I think we're confusing something here. The nominal refers to the input voltage, right? So input voltage, or the rated output voltage is always given in or at nominal input voltage. Right? Okay. Now, the value that you see, let's say you buy a DC to DC converter, they're gonna give you a round number, like 12 volts. They're not gonna give you 11.95, right? Or 12.01, right? This is like a spec that they trying to target, right? And you'll see that it is very tough to get exactly 12.00, right? So this is like their targeted spec. But when you actually measure the output voltage at nominal input voltage, then you'll get slightly more or slightly less than 12 volts. Does that make sense? In this example, I just give you 12 to make it easy. Does that answer the questions? These are all good questions, so make sure that it's clear. Okay, good. All right. Moving on. Okay, so then let's say that you're designing a DC to DC converter, but then you want to be able to, what's the word I'm looking, predict line regulation. Can you do that? Because this equation that I give you earlier, right here, this can only be done if you have the prototype in front of you, right? Or you have the DC to DC converter in front of you. Then you can go to the lab and get these numbers, right? But what if you are designing a converter and you want to be able to predict the line regulation before you build it? You could by using the following method right here. Percent line regulation is equal to, I'm just going to give you the final equation, partial derivative of V out with respect to V in times V in over V out. Okay, so we could calculate line regulations beforehand, before we build the prototype. Okay, so here's the equation. Multiply by 100%, that gives you percent line regulation. Let's look at an example on how to apply this equation. Let's say that I have a circuit. It doesn't have to be DC to DC converter, right? This is just to show you how to apply this equation. Let's say that the ratio of the output voltage over the input voltage, V out over V in, is equal to R out over R in plus R out. Are you familiar with this equation? Have you seen this equation before?
voltage divider?
Yes, it is voltage divider. Yes. So remember that this is an equation for voltage divider. This is your V in, and here's your V out, right? And here's your R in, here's your R out, right there. Exactly is the equation for voltage divider. And let's take a look at percent line regulation of a voltage divider, shall we? All right. So that's the equation for V out over V in, right? That's easy. Rewrite. So I'm going to rewrite V out in terms of V in. Right? That's the first equation I need. And then the reason why I need this equation, because I need to take partial derivative of V out with respect to V in. Right? And so everybody should know how to do this. That's just going to be the constant. This is our constant right there. And that's why when you take partial derivative of V out with respect to V in, you get that constant. Okay. All right. And then what else do we need? The equation is asking for partial derivative of V out over V in, or with respect to V in, sorry, and then times V in over V out. Do we know this ratio? Yes, we do, right? If you go to the previous page, that's V out over V in. So how do I get V in over V out? That's just the inverse of that, right? So that's what I did right here. V in over V out is just the inverse of what's given. So guess what happens here? When you have a voltage divider, once you calculate percent line regulation, the result would be 100%. Now tell me if this is good. The answer is there already. Sucks. I already answered that question that this is bad for DC to DC converter. Why is that? Anybody?
It means that the output's going to change a lot.
Mm-hmm. Yeah, exactly. So 100% means this. Anytime the input is being changed by a certain percentage, then the output will also change by the same percentage. That's what it means. So if the input is being changed by 10%, then the output will also change by 10%. That's not going to be a good, voltage regulator, right? Because it's always changing based on input voltage. In fact, it's tracking the input voltage very nicely, right? And that is the main reason why a voltage divider is a very good voltage sensor, right? If you look at this voltage divider, if you want to sample this voltage divider is a perfect voltage sensor for us, right? Because if the input voltage here changes by 25%, V out will also change by 25%. Would that be ideal for a voltage sensor, right? That's why in DC to DC converter, we use this a lot. And you're going to practice using this as well in the lab today, right? Using voltage divider to change the output voltage, basically changing the sensor. Okay, that's the reason why it is a very good sensor for voltage, because it has a line regulation of 100%. Very bad for DC to DC converter, but good for sensor. Okay, any question on that one? Now let's move on to load regulation. Now, in the previous test, you are changing the input voltage, right? And again, output voltage needs to be maintained at a certain value, constant value. Another test would be, what if I keep the input voltage the same? Let's say nominal value, right? Keep the input voltage the same. However, what I'm going to change now is the output current, is the energy demanded by the load. So what if the load fluctuates? That is also practical, isn't it? Because we know that load is not going to ask for a constant current every time, right? For a certain load, yes, but majority of the loads, they would require different current at any given time. So therefore, it is a very useful test to be able to determine how output voltage can be maintained at varying output current. Right? So that's called load regulation. And now you understand why it's called load regulation. Right? Load means the output, right? So what happens with the output voltage when the load is being changed or varied, right? So again, refers to the ability of power converter to maintain the output voltage even when the output power fluctuates. Reflects changes seen at the output caused by altering the requested energy flow. How do we calculate this? Again, these are all measured at nominal input voltage, okay? Nominal input voltage. So percent load regulation is equal to V out average, again, output, okay? Output voltage at low load, load means current, minus V out average at high load. Load means current again, divided by V out average output voltage at high load. Okay, high. So these are the same value. This value and this value, they are the same. So you only need two numbers for this test. Unlike the previous test, right? The previous test, you need three numbers. Here you need two numbers. Average output voltage at low load, average output voltage at high load, and that would be it. Now, how do you define high load and low load? This is something that you have to determine yourself. Sometimes the customer will ask you will give you the numbers, but at other times you have to determine yourself based on inductor current, and we'll talk about it. I don't think it's going to be today, but next week, right? So based on continuous conduction mode, you have to be able to test the load regulation while the inductor current is maintained at continuous conduction mode operation. Don't worry about it for now, but yeah, this low load could be different numbers. It could be 0%, it could be 10%, right? The high load is always 100%. At least based on my experience, the high load is always 100%. But you know, maybe the customer wants you to be to give you a different value. Let's say 90%. Right? In that case, that's what you put. Okay. Any question on that? All right. Here's the diagram to show you what you need to do for load regulation measurement. V in is at nominal value, right there, nominal value. Okay. So keep that at nominal value at all times. And then what you do here is that you change the load right there. Right? In our case, if it's in the lab, in power electronics lab at Cal Poly, we would change the electronic load setting, right, from low load to high load. This is actually backwards. Sorry about that. The low should be down there, the high should be up there. Sorry about that. You get the idea. Well, actually, no. This is actually pretty accurate now that I think of it, because I'm drawing it in terms of resistor. So when the resistor is low, when the resistor is low per given output voltage, then that gives you the highest current. When the resistor is high, then you get the low current. So this is actually good. Right, that's okay. It's actually good. All right. Then what do? At low load, you measure output voltage. At high load, you also measure output voltage. So those output voltages that you measure, average values, those are the ones you put into the equation. Okay. Here's an example. A DC to DC converter is rated at 15 volt at 20 amps, 26 volts to 30 volts, input with nominal value of 28 volts. Find its load regulation if at 0 amps, 0 amp, load voltage output is 15.5 volts, and at 20 amps, output voltage is 14.85 volts. Both are measured at 28 volt input. Okay, so let's take a look at this problem. Rated at 15 volt, that means that's the output voltage, 15 volt, nominal value. And then full load current of 20 amps, input voltage main, V in max, with a nominal value of 28 volts. So we need to use this, right? For load regulation, we need to use nominal input voltage. Okay, let's see. Find its load regulation if at 0 amps, output voltage is 15.5 volts. So that's at 0 amps. And then at 20 amps, so that's 100% load, isn't it? See right there? That's 100% load. So looks like for this example, I'm using 0% to 100% load. Right? At 0% load, output is 15.5. At 100% load, the output voltage is 14.85. So I'm going to use these two numbers right here. Remember, I'm only using V out numbers, these two numbers. So 14.85 right there. And then there you are, there. 15.50 is right there, okay? And then just like the equation shows you, the 14.85 you also put on the denominator. That's at high load. Then you get the number for load regulation. Any question on that one? All right. If not, then just like line regulation, can you predict load regulation? The answer is yes. Right. Again, this equation that I gave you earlier for load regulation, that can only be done if you have the prototype in front of you. Then you can go to the lab and test the prototype, or you have the DC to DC converter that you purchase in front of you, and you can do the test. What if you're still designing it and you want to predict load regulation? You could. This is the equation for percent load regulation right there. Right. Partial derivative of V out with respect to I out times I out over V out calculated at V in equals to 0. Right. That's a mathematical definition of load regulation. Let's take a look at how we apply this equation to another circuit. Well, I don't know if this is another circuit. Maybe you know this as well. The output input ratio of a circuit is found to be this equation right there. Have you seen this equation before? Where is that coming from? Any guess? No? No? Interestingly, this equation comes from a voltage divider as well, right? You are all familiar with this voltage divider that I'm gonna draw right now, right there. I'm drawing that right now, right? That's your R in, that's your R out, right there, right? This equation comes from the same circuit, except what? Except this voltage divider now is being loaded at the midpoint. So I'm gonna draw current from there, right? So there's a load connected to the midpoint. Okay, so that's called a loaded. This is a loaded voltage divider. Okay, you're all familiar with voltage divider without loading it, right? Without this current, or I out is equal to 0, basically, right? Your I out is typically the same as this current right there, current to R out. But now I'm actually pulling current from the middle point of these two resistors, okay? So if you do that, then the equation for V out over V in, this is your V in, here's your V out, right there, is going to change, right? If it's not loaded, that means what? I out is equal to 0, right? If it's not loaded, go ahead and plug in I out equals to 0 there, and you end up with the same equation that we saw earlier. Right, the standard voltage divider that you know, right? If I out is equal to 0. But notice that once you load voltage divider, then V out is no longer just a function of V in. It is also a function of I out. You can see that from here. See that? So now V out is a function of V in as well as I out. Right? It becomes more complicated equation. Any question on that one? All right, so here's the equation for V out of a loaded voltage divider with respect to V in and I out. Okay, let's determine the load regulation here, right? Okay, as you are changing I out. Okay, just following this equation right there, I need to find partial derivative of V out with respect to I out, and then I out over V out when V in is equal to 0. So there are two terms that I need to do here. The first term, the second term right there. Okay, let's do that. First, V out over I out. Any questions? Okay. So V out over I out is equal to V in over I out. How do I get this? Is that from the equation earlier? V out over, what is it that I do here? V out over I out, V out over I out. So V out over I out. So I'm going to divide both sides by I out, looks like, right? So divide both sides by I out, then you get, let's see if I, yeah, it is correct. So if you divide both sides by I out, then you get this equation right here, right? And then if you apply V in equals to 0, then this disappears. Now you get V out over I out equals to this equation right there. Okay, all right. And then I'm going to rewrite the equation from the previous slide right here, rewrite this equation, right? And you get this expanded version of the equation. See that? That's the same equation, right? And then the reason why I want to do this, because I want to take the partial derivative of V out with respect to I out. If I take a partial derivative of V out with respect to I out, that means V in, you treat it as a constant, right? So therefore this goes away, right? This goes away, and you only end up with the constant portion of I out. That's what you see here, okay? So now I have the two terms, right? I just need to plug in those terms into the equation for load regulation, right? And turn out to be 1, right? 1, if you convert it into percent, it's going to be 100% as well. So what do we learn about a voltage divider when you load it? It's also bad, right? Right there, because the load regulation is 100%. What does that mean? Load regulation of 100%. It means that as you are changing the load by a certain percentage, then the output voltage also changes by the same percentage, okay? So if the load is changed by 20%, current in this case, load means current. If the output current is changed by 20%, then output voltage will also change by 20%. Not good for DC to DC converter, okay? Now you know the reason why you should not use voltage divider as a DC to DC converter, even though it is a DC to DC converter, isn't it? Right, because you have DC input to the voltage divider, and you have DC output on the bottom resistor. So theoretically speaking, it is a DC to DC converter, but it is not a good one for power converter, right? For converting power, it's not really a good converter to use, right? Problems are line regulation is 100%, load regulation 100%, and of course efficiency is going to be very low, as we are going to see next. Okay, example of data sheet that provided regulation data. You can see I copy pasted from a DC to DC converter off the shelf that you can purchase commercially. And you can see the line regulation and the load regulation right there, the numbers that they are providing, different part numbers, right? Different DC voltage out. Okay, now you know these numbers. Now you know what these numbers mean, okay? In case before you're wondering what they are, now you know. Okay. All right. Any question on this? No? All right. Notice that they always give you round number, just like I said earlier, 5 volt, 12 volt, 24 volt, 48 volt, even though when you actually measure it, it's not going to be exactly 5 volt at nominal input voltage. Not going to be exactly 12 volts, right? But these are just, you know, standard, what do you call it, voltages that loads are typically needing for DC to DC converters. These are all targeted values. All right. Okay, next, cross-regulation. Any question before I move on to cross-regulation? No? All right. The next one is cross-regulation. This only occurs when you have transformer in the converter. So this relates to next chapter where you use transformer in the converter, right? So what happens is this, okay, I have the explanation up there, but I'm just gonna explain it based on this diagram, right? Let's say that you have these isolated topology. That means you have transformer here, secondary winding right there, and the primary winding right here, all coupled, magnetically coupled, right? And from one source, you can actually provide two outputs, the first one and the second one, right? Right. So the primary output is where I put feedback. So you can only, unfortunately, you can only have one feedback into the converter because there's only one switch, right? Or a couple of switches that belongs to the primary side, right? So therefore, you can only have one output that has the feedback loop. That means the other output, the top one, right, is not being regulated well. Okay, because there's no feedback there. Okay, now, if that's the case, if this is the case that we have, then what happens if, let's say, the input voltage changes? What's going to happen? Well, if the input voltage changes, then this feedback right here will sense it, right? If input voltage changes, then the output voltage of the bottom one will sense it, right? Because then it'll say, oh, input voltage is now higher. How does it know it? Because the output voltage gets higher, right? So therefore the feedback senses it and then say, okay, let's reduce duty cycle, right? So that's good. What about the top one? Same thing, right? Because the input voltage is changed, output voltage on the top one also changes, right? But then it's being helped by the bottom one, right? Again, as an example, if the input voltage goes up higher, duty cycle is going to go down, right? Based on this controller, both of these are going up, right? So even though only the bottom one that's sensing it, but the lower duty cycle will affect both the top and the bottom, right? So that's good, right? The lower duty cycle will change the lower output voltage as well as the top output voltage. Again, because the top output voltage is being controlled by the same duty cycle as the bottom one, okay? So that's good still. What about if the output, let's see, what if, what's the second one? The second case would be, let's see. Yeah, what if the top voltage right here, what if the current through the output, through the top output increases, let's just say. So a change in the output current of the top power supply. What's going to happen? Well, of course, V out is going to change, right, accordingly. If I out is getting higher, then output voltage is going to go lower. It's going to drop, right? Now, if that's the case, is there a mechanism for to fix this output voltage? The answer is no. Like there's no feedback, right? So unfortunately, the output voltage will be lower because of this change. However, if you look at the bottom power supply, when the output current changes on the top power supply, would that affect the bottom one? The answer is no, right? Because the duty cycle is being controlled by the bottom power supply. So therefore, any change on the top power supply is not going to be sensed by the bottom one, right? So therefore, even though it's not good for the top one, but for the bottom one is not being affected. So at least for that one is okay, right? For the bottom one. Now, one more case. Okay, I'm going to erase this. What if the change occurs at the bottom power supply right here? Again, let's say that I out goes up. That means V out drops, right? But that's going to be dropping, the output voltage on the bottom supply is going to drop temporarily, right? Why? Because as soon as it drops, it's being sensed by the controller. and then duty cycle will be increased because of that, right? And so that's going to fix this output voltage. Agree? Good, right? So then that's good for the bottom one. What about the top one though? That's not good news for the top one, right? So any change in the current or in the output voltage of the bottom one will also change the top one, right? Because any change on the output voltage of the bottom supply right there will change the duty cycle. If duty cycle changes, it will be good for the bottom one. But look, the top one is not requiring any change in the output voltage, but now it's being forced to change because it's sharing the same duty cycle, right? The same duty cycle is being shared for both, right? So that's not good for the top supply, right? Any type of changes on the output voltage here on the bottom supply will also change the top supply. So that's called cross-regulation. That's called cross-regulation. Okay, so that's the type of problem you'll be coming across if you have multiple output voltages from the same input voltage. Any question on this? No? All right. Next, peak-to-peak output voltage ripple. It is a measure of repetitive or steady-state small deviation in output voltage, typically given in percentage of average output voltage. All right, right here. So first you would calculate peak-to-peak ripple, and then you divide it by average of the output voltage. These are all measured, okay? Measure peak-to-peak, measured average output voltage. This is typically, I forgot to go ahead and add this into your notes. This is all done at full load. Why? Because that's where you have the worst case peak-to-peak ripple. That's when you get worst case peak-to-peak ripple. So you measure at full load, right? And typically you also use B in nominal. Okay. All right, so here's an example. So the equation is simple, right? Peak-to-peak ripple divided by average voltage times 100%. Here's an example. Let's say that this is the output voltage, and if you zoom in, that's the fluctuation on the output voltage right here. Then you would measure the fluctuation, right? That's just going to be 5.1 minus 4.9, right? 5.1 minus 4.9, and then divided by the average value. Average is 5.0 right there. So if that's the case, then what is the percent peak-to-peak ripple? 5.1 minus 4.9 divided by 5 volt times 100%, that's 4%. Okay, any questions on this? Okay. If not, let's move on to the next one. This is the last test. This has to do with controller test, right? Very common test as well to make sure that the converter that you are designing or that you're purchasing is stable. This is usually the very last test you want to do. The previous tests, these are all steady state tests. This is the transient test. This is stability test, right? It is a measure of how fast the converter responds to a step change in the load. The measurements are typically done for both a step up as well as a step down changes. So step up, step down. You learn this from EE410. Remember step up, remember step response, right? A step response could be a step response upon a step up change or a step down change. Now, the level of stepping up and stepping down is up, really up to you or up to the customers. Right? Sometimes you go from 0% to 100% or 10% to 90% and vice versa. Right? So here's an example. I'm just creating a step down, looks like. LT1170 from ADI, simulated with LT Spice. And notice I introducing a step on the load right there, right? So here's the step. This is output current. The blue is output current. The green is output voltage, right? So you could see the transient response, right? As you are stepping down the current, the controller reacts, right? This feedback right here reacts to it. Right? It reacts to it, and then luckily it's stable. That's steady state, so it's stable. It's good. Right? That's called what? Percent overshoot. Remember that? That's also called settling time. Remember settling time? Now it's all coming back, right? Now you actually get to use those things that you learned from 302, percent overshoot, settling time, right? And yeah, we do want this to be stable, right? If it's not stable, then you'll see something like this. That's called marginally stable, right? If that's the case, then yeah, you need to fix the compensator. Again, beyond the scope of this class, okay? That's what you hope to see, steady state. That is stable right there. Right? Now you can see that as current drops, voltage goes up. Does that make sense to you? To me, it does, right? Because less current means what? Why is it not coming down? Why is it not doing this? Why is the output voltage not doing this?
Because you're still supplying power.
In both cases, you are still supplying power, but why is the direction of the voltage goes up first instead of going down first? So this has to do with Ohm's law, right? Because between input and output, you have drops, right? You have drops due to those components, non-idealities of that components. So if the output current goes down, then by Ohm's law, just roughly I times R, if you can, roughly, right? Model this as a big R in between input and output, then you could see why, as current goes down, I times R drop between input and output goes down as well, right? For the constant input voltage, if the drop between input and output goes lower, of course, output voltage goes higher.
Professor,
does that make sense?
Are you saying that's primarily because of the inductor?
No, many things, not just inductor. Inductor is one of them. We have RDS on of the switch. We have the on forward voltage of the diode. So many things. And ES out of the cap. That's why I'm just gonna lump them together into just one R. So that you'll see that between input and output, there's a drop. That's gonna be a function of resistance within the circuit, right? So again, if the output voltage goes down, that means that I in the middle is going to be going down as well. So I times R drops, right, in the middle. So if I times R drops in the middle, that means per given fixed input, output voltage will be higher, wouldn't it? Hopefully that makes sense, okay? So if I do the step up right here, unfortunately I did not, if I do step up, then you'll see that the output voltage goes down first before it goes back to the nominal value. Okay, any question on this?
Can I ask a quick clarifying question?
Sure.
Are you saying I is increased for that hump in voltage?
This is voltage. This is voltage, not current. This is voltage.
No, I'm asking if an increase in I is causing that increase in V, or is if it's an increase in R in the beginning.
I don't understand the question. Go ahead, ask again.
So in that hump, is V increasing because I is increasing?
I is decreasing. Look, I goes from here to here. Step down.
Oh, okay.
Yeah, you are stepping down the current. Right? You're stepping down this output current right here, right there. So as a result, the drop between input and output will be less as well, right? Because the drop between input and output goes down, then of course for the same input voltage, output voltage goes high, right there.
Okay, thank you.
Yep. So V out is roughly, this is not exact equation, okay? V in minus the drop in the converter, something like that, right? So V in is fixed. So if the drop is lower, of course, V out gonna go up high. Right. Any questions? Any other questions? Okay. All right. So yeah, if somebody asks about why the voltage goes up as you are stepping down current, now you know. It's going to be the opposite. Okay. If I'm stepping up current, then voltage is going to go down, right? Because then you have more drops within the converter. And I have the explanation here, by the way. Okay. So you can see that the my textbook is I'm trying to be as very as practical as possible, unlike regular textbooks. Regular textbook just talks about all theories, but this is a learn by doing school, so I like to throw in some practical issues in my book, right? So hopefully it serves as a good reference as well. Once you go out there and work for a company, hopefully you get to keep the book and use it as a reference, right? Okay, what's next here? Alternatives to DC converters. I'm going to go through this quickly. Okay, I'm going to try to finish these three quickly because we all know about these different methods already. Voltage divider, we talked about it, right? So that's a DC to DC converter. In theory, it is, right? V in is DC, output is DC. So yes, we do have DC to DC converter. What is the problem? We already saw two problems. What are those? 100% line regulation, 100% load regulation. Not good, right? What else? Power loss, right? Because current has to flow through these resistors, right? Or at least one resistor on top right there. If you are loading it, at least current will have to flow through here. That's going to burn power, right? So your efficiency is going to go low. But what is the efficiency if you're not loading it? If you're not loading it, but what if you don't have these branching out right there? So this is your load right there. So what is the efficiency? It's right here, right? P out over P in, that's the same definition, right? V out times I out over V in times I in. Notice that if I don't have this branch right there, I in is the same as I out, right? If I don't have this branch, forget about this, right? Then I in is equal to I out. That's why when you derive the efficiency, I out cancels with I in, right? So therefore, the efficiency equation is V out over V in, which could be good, right? How is that good? If what? If V out is very close to V in. If let's say that your V in is 12 volts, your output is 11.5, then of course good. But in reality, that's not going to happen, right? Output voltage is typically quite different from the input voltage. So let's say 12 to 5, right? 12 to 3.3, 12 to 2.5, and go ahead, crunch those numbers. That's going to be a very low efficiency, right? If output voltage is, let's say 5, input voltage is 15, that's 5 over 15. That's 1/3. That's what, 33.3% efficiency, right? That means you lose 67%. Is that good? You already know that's not, right? So that's why this is not a good equation to have, right? Ideally, it's already V out over V in. Again, it's only good if the output voltage is very close to the input voltage. Okay, but it is very good for sensing, as I said earlier. Now, what if I load it? Where is it? Right here. I'm going to erase this. So now the load is right here. Right? Then clearly I in is not the same as I out anymore, right? This is I in right there, right? And here's I out right there. So they're not the same anymore. So then we have a different equation. I won't go through the derivation, but here's the efficiency when I out is not equal to 0. Right there, it's a long equation, okay? And you can see from this equation that if the output current is higher, the efficiency is going to be smaller. And I do have the curves for this. Let me skip ahead on this one, right there. So you can see efficiency versus normalized output voltage, right? So you can see that the blue one right here, that's loaded, right? That's loaded, and The straight line one, that's the not loaded one. That's V out over V in. That's why it's a linear curve. Whereas the loaded one is actually worse. Look at the maximum efficiency for the loaded efficiency. 0.5, that's the best you can get if you're loading it, right? That is not good, right? The best case is 50%, okay? For a not loaded one, it could be 100%, as you can see. But that requires output voltage to be the same as input voltage. That's why the ratio is equal to 1 right there. This is V out over V in, okay? But again, as I said earlier, in practice, typically the ratio is not gonna be close, right? It's gonna be around 0.4, 0.5, and so on and so forth, right? Okay, so that's why a voltage divider is not good for DC to DC converter, but it is very good for sensing voltage. That's why in DC to DC converter, as some of you will practice today in the lab, the rest of you on Thursday, you can see that we are using voltage divider to sense the output voltage. Perfect for sensing output voltage, right? Any change on the output voltage will be reflected by the same percentage at this midpoint. That's what we use to send signal to our controller, okay? And make sure that these resistors are big, right? You can see these resistors are big, kilo ohms. Otherwise, you're loading this, right? Instead of loading the load, current flows through here. So you don't want that. You don't want current to flow here, okay? Okay, next. So not good, okay? Voltage divider is not good. Same as linear regulators, right? We learned about linear regulators in one of the beginning chapters. I don't remember which one, but same thing. If you have a linear regulator, you basically biasing the transistor so that it has different drops. Well, that's just analogous to having voltage divider. When you have voltage divider, then you already know the efficiency, right? The ideal efficiency is V out over V in. Right there. So the same equation, V out over V in. So keep in mind, if you are using linear regulator, including LDOs, okay, then your efficiency is V out over V in. Okay? Now, why is it that people still using linear regulators or LDOs? The reason being because this is still okay, right? This low efficiency, it's still okay if what? Anybody can guess?
If you need a really like low noise signal, or your current's low. I mean,
there you go. That's what I'm looking for. Yeah, that's what I'm looking for. So many people are still using linear regulators because the output current is very tiny, or the output power, I should say, instead of output current, output power is very small, right? If the circuit is only requiring 10 milliwatts, so who cares about 50%, right, of 1 milliwatt, right, compared to the big ones, right? So they're still using this for low power applications. They still use linear regulator right here, okay? And it is still being used for DC to DC converter, again, as long as the power requirement on the output is very low, right? To the point that, losing 70% of 10 milliwatts or 70% of 1 watt, for example. Let's say this is a 1 watt converter. You lose 70%. That's still 0.7 watts, right? Relatively speaking, if the system is 1 kilowatt, then 0.7 watts out of 1 kilowatt, probably is nothing, right? So, you decide whether or not your load can actually use a linear regulator or LDO, or is it better to use switching regulator? So you decide when the output power is low. Okay. If again the load requires very low noise, so low power and low noise, then yeah, definitely you want to use this linear regulator. Any question on this? Lastly, of course, this is what we are going to discuss. The first topology is going to be discussed next week. Switching mode DC to DC converters, right? You can see already that's the disadvantage is that it's more complex circuitry than LDOs or linear regulator, right? You start from simple concept of having a switch between input and output, as you already know, right? So by pulsing the switch here. When pulse is high, you turn on the switch. Pulse is low, you turn off the switch. And then you can adjust the average output voltage, right? And flow and deliver power to the load very efficiently doing it this way, right? And I won't go through this anymore because I did that in the beginning of the quarter. But if you do that, then you get output voltage that is pulsating as well, right? So this is output voltage, okay? When the switch is on, output is high, switch is off, output is 0, right? And then you're looking for the average voltage. And if you take the average equation of this waveform, then you get output voltage equals to input voltage times duty cycle. Where is that at? I thought I have it here. Oh, right here. So our average output voltage right there is equal to input voltage times duty cycle. And you know what duty cycle is? That's the ratio of on time over the period. So on time is the pulse width right there, right? From here to here is on time of the switch divided by the period, which is from here to here. So the ratio of pulse width and the period is called duty cycle. Well, we also know that the inverse of the period is switching frequency. So by looking at this equation, I know there are two ways. There are two ways to adjust duty cycle. Number one is by adjusting T on, keeping frequency the same, right? I could do that. If I keep T on the same, switching, sorry, what did I say? If I keep switching frequency the same and change T on, then I'm adjusting duty cycle. I could also do the opposite. I'm keeping T on the same, but then change switching frequency, and I can also change duty cycle that way. And if you do the first method, I believe that's what I did, or this is actually the first method. If you do keep the switching frequency the same, you can see from the period, if the period stays the same and you're changing the pulse width to bigger, bigger, and biggest, then you're adjusting a duty cycle from small to large, right? That's called PWM if you do it this way, right? So fixed switching frequency, changing T on, that's PWM, pulse width modulation. Whereas if you do the other way, you are keeping T on, but then you are changing T. You can see the T changes from here to here to here. You can see T becoming smaller. When T becomes smaller, that means switching frequency gets higher. Then you're also adjusting duty cycle from small to large, the same effect. Right? This method is called pulse frequency modulation. Right? Which one is more commonly used? Pulse width modulation. Right? Pulse width modulation is commonly used. Why? Because switching frequency is fixed. Imagine a filter, designing the filter for PFM. It's going to be tough, right? Because the frequency is changing to try to regulate the output voltage, right? However, pulse frequency modulation is known to have higher efficiency at low load, like this one right here. Imagine if it's a low load, light load, then I could spread the period far apart, right? Instead of the same period. So that would require smaller power consumed by the controller, right? So that's why nowadays it's very common, very, very common nowadays for a controller to have a hybrid type of techniques. So at low load, they do PFM. At higher load, they do PWM, right? That way they can keep efficiency high, even at low load, okay? And they don't necessarily call it PFM. Sometimes they call it, something like burst mode, which is very close to PFM, right? So if you see, the word burst mode is close to, it's not really exactly the same as pulse frequency, but the concept is the same, right? As pulse frequency modulation, okay? So now you know when you hear the term burst mode controller, that means at light load, it's changes its mode to burst mode. Higher load, it goes into PWM mode. Okay. All right, almost done here. And then there's also a different type of controller called hysteretic controller. It's using, what do you call it? Limits, high, limits low, right? High limit, low limit. So you can see here's the feedback, sensing the output voltage, and this this comparator right here is a hysteretic comparator that has, you know, top limit and bottom limit. So if the output voltage hits the top limit, then the duty cycle says, hey, close the, or not duty cycle, controller says, controller will ask the switch to turn off. When every time it hits the upper limit, turn off the switch. When you turn off the switch, inductor discharges. Until when? Until it hits the lower limit. Right? When it hits the lower limit, then the controller says, turn on the switch again. You know, when you turn on the switch, then you charge the inductor again, and so on and so forth. Okay. Now notice that the smaller the window here, if you make it smaller, the faster it will switch, right? So be careful with hysteretic. Okay. Again, because the smaller the window, the faster the switching frequency. So again, this is almost like PFM. Your frequency spectrum is going to be all over the place if you keep changing the frequency. Okay. These are the different controllers that you can purchase out there for different for different techniques: PFM, PWM, hysteretic. Just in case in the future you need to use any one of these. These are just some examples, right? I didn't list all, but you get the ideas here. Okay, these techniques are being used commercially. These different techniques: PFM, PWM, and hysteretic. Okay, that would be it for today.